Okay, development does not end once we have a structure that looks brainish. Once we have the brain, development continues for quite a while. There are a few things that have to happen. First of all, we still have to make more cells. As you saw, the telencephalon, the cerebral cortex, takes a lot of cells, and those cells are continuing to be made up until birth. And then in the hindbrain, about half of all the neurons in the brain are contained in the cerebellum. And those neurons get born primarily after birth. So for several years after birth, babies are making the neurons for the cerebellum. No surprise that a 5-month-old is not as coordinated as a 10-year-old or an adult, because the cerebellum is simply not even structurally complete. Once all the neurons are made and the structure is complete, development still is not over, because we have to hook up the brain correctly. We have to get the physiology correct. We have to make sure that the right neurons are talking to the right audiences. And we do that through the general way that the nervous system does this is to make lots and lots of connections, exuberant connections, and then prune them back, take away some. So you make a lot, you decide which ones are good, strengthen those, and let the weaker ones, the less useful ones, die back. It's called synaptic pruning. And we might start with all of these inputs, a blue input, a yellow or orange input, and a yellow input, and then with some amount of time, these are going to die back, and now this neuron is only going to be listening to this neuron, to this input. So, how does that make a difference? Well, there are several diseases that where a disorder of synaptic pruning or synaptic pruning does not occur normally, and that produces a dysfunction or a condition. And one of them is autism. Autism is thought to have a contribution. One of the problems in autism is thought to be a problem with synaptic pruning. Another one is cerebral palsy. And cerebral palsy is pretty darn common. It affects roughly 2 out of 1,000 kids. And so I thought it would be useful just to go into that a little bit more. Now, what we have here is just a schematic of the corticospinal tract. We talked about that in the last segment, I believe. So this is the tract that carries motor information from the cerebral hemisphere down to the spinal cord to a motor neuron that then innervates a muscle. So Simon says, raise your hand. That information has to go from the other side. So if I want to raise my right hand, information has to come from my left hemisphere to my right spinal cord, to a motor neuron in my right spinal cord, and then out to a muscle on the right side of my body, in my arm. But that's not how it starts. It actually starts with input from both sides, from both the left and the right motor cortex project to the motor neuron. They're both telling the motor neuron what to do. In normal individuals, this same side input starts to die back during development. And then by the time the child is a child out of being a toddler, this is now retreated, and it's no longer, this motor neuron is getting one input instead of 2 inputs. It started with 2, but there was synaptic pruning, so now it only listens to one drummer. It's only listening to the correct side, the motor cortex. This is the normal situation. In the situation with cerebral palsy, there are a variety of types of cerebral palsy, but in one type called spastic cerebral palsy, which is due to injury to the motor cortex, what happens is that these motor neurons receive input from neurons in both sides. So, and that persists. It never goes away. So this is the start, and this is in the adult. In the adult with cerebral palsy, the motor neurons are getting input from both sides of the cortex. And the result is that the circuits down in the spinal cord and even the muscles change their properties. And there are enduring, permanent changes that occur in motor function. So the important thing about understanding cerebral palsy is that it is a developmental disorder. It happens during development, but it is not a progressive disorder. It does not change. Once the initial insult has happened, it is a permanent disorder. The implications of the problem may change across the life cycle, but the actual neural changes don't change. Cerebral palsy is only a deficit in any of the motor circuits. So it can be, for example, most commonly perhaps damage to the motor cortex, but it could also be damage to the basal ganglia. It could be damage to the cerebellum, produce other types of cerebral palsy. Cerebral palsy can produce can have a severity that ranges from very mild, almost imperceptible, to completely debilitating or very debilitating, challenging, shall we say. And so in one of probably the most common form of spastic cerebral palsy is a scissoring gait. And all it is that the two legs are what are called adducted. They're brought in. And so the gait's off, but these people can get around. And notably, in this and other forms of cerebral palsy, there is no necessary impairment in intellectual ability. You can have a bigger insult to the brain that does produce intellectual impairment, but the default is, the typical situation is that a person with cerebral palsy does not have an intellectual disability. In this case, the only problem, the only non-typical issue that a person with scissoring gait has is this abnormal gait. And on the other hand, it can be extremely debilitating. It can make a person depend on a wheelchair, for example, for mobility. And this is one of our wonderful MOOC students from a couple sessions ago. And Laura has cerebral palsy. And I show this picture simply because Laura is an example of a person with severe cerebral palsy who's living a fabulous life and having a good time. I'm in regular contact with her, and she's a happy person. So these diseases are they're profound, and yet they don't need to define a person's take on life. Okay, great. So that pretty much does it for development, and we're going to move on and look at neuroanatomy.